Okay, after designing for flexure and obtaining that we only needed the minimum reinforcement, 2 number 9s, we proceed to design for shear and torsion. The first thing we do is that we check that the dimensions of the beam are adequate to resist the combined shear and torsion. To do that, ACI 11.5.3 provides us with this formula to perform that check. I'm not going to show you the details of that calculation, but if you put in all the values, you obtain that the left hand side is 212, the right hand side is 470, and so this means that the dimensions of the beam are adequate and we can proceed to design the reinforcement. For torsional design, the first thing that we're going to check is the threshold torsion. If the applied ultimate torsion value is less than the threshold torsion, then that means that the beam doesn't need to be explicitly redesigned for torsion, and it doesn't need any specific detailed torsion reinforcement. If not, then we need to proceed and design torsion reinforcement. So this is the formula for threshold torsion right here. And for that formula, we need the area of the cross section, which is ACP, and that area can be found by looking at the cross section here on the right, which is 20 times 30 plus 12 times 12. 12 times 12 is the area of the little lip on the right, the bracket there, and so that gives you 744 inches square. PCP is the perimeter, and that can be obtained by simply adding all the sides. So that would be 30 plus 20 plus 18 plus 12 plus 12 plus 32. That's what we have right here. And we obtain 124 inches. Those numbers are substituted in the formula with F prime C equals to 4,000 and phi equals to 0.75 for torsion, and we obtain a threshold torsion value of 17.64. That number compared with 57.6 we can conclude that beam needs torsion reinforcement. And so we are going to go ahead and do that. But before we do that, let's do a shear capacity check. This is to determine if we need additional reinforcement for shear. In this case, we're going to compute phi VC, which is the shear capacity provided by concrete. As long as we provide the minimum shear reinforcement, we can use this concrete capacity. 2 square root F prime C BD. In this case, B is B web, which is 20 inches, and D is 27.4. If we do the calculations, we obtain a value of phi VC equals to 51.9. That value, compared with 43.2, which is the ultimate shear on the beam, we can conclude that the beam does not need more than the minimum shear reinforcement, so only needs minimum shear reinforcement. The next step is to check torsion reinforcement. To do that, we have to satisfy this formula, which is phi T sub n greater than Tu, the typical design formula. And so that formula is phi times 2a naught times at fyt cotangent of theta divided by s. And Tu is the value of the ultimate torsion that we already obtained before, which is 57.6 from our analysis. From here, what we are interested is in determining At over S, which is the amount of torsion reinforcement per spacing. And so we are going to solve for that from this formula here. A naught is 0.85 A naught H. A naught H is the area enclosed by the center line of the closed transverse reinforcement. And by looking at our cross section and knowing that we have 2-inch clear spacing to the longitudinal rebar, and we are going to most likely end up using number 4 transverse reinforcement. From that we can obtain that the dimensions of AOH are going to be 16.5 times 26.5. That leads us to an A naught of 371.66 with cotangent of theta equals to 1, given that theta is 45 degrees because the beam is non-pre-stressed, and the yield stress for steel is 60 ksi. If we do that, we solve for At over S, which is 0.0207 inches square per inch. So that's the amount of reinforcement per leg that we need per spacing. You can do the numbers and you can see that this can be obtained with a number 4 rebar spaced at 9 inches. For the minimum reinforcement, just to make sure that we're covered in that regard, we check the ACI's formulas, which says that 2 times AT plus AV has to satisfy these minimum requirements shown below. Since we don't have any need for transverse reinforcement due to shear, we are just going to add 2 AT. And we said that we had number 4 at 9. So that's 2 times 0.2. That gives us a value of 0.4 inches square. And that is significantly larger than the minimum requirement. So we are okay with transverse reinforcement. That will cover torsion and shear. For the longitudinal reinforcement needed for torsion, we are going to use the formula that I've presented in previous lectures, recommended by ACI, which is this right here. And we have AT over S times PH times the ratio of FYT and FY times the cotangent square of theta. This ratio here is 1 because we're using the same reinforcement for transverse and longitudinal. Both have 60 ksi yield stress. And since theta is 45 because the beam is non-pre-stressed, this is also 1. So AL simplifies to this equation down here, which gives us 1.91 inches square, which is approximately 5 number 6. So, in summary, the design of our beam requires 2 number 9s for flexure at the top, stirrups number 4 at 9 inches on center for shear and torsion, and 5 number 6, which are going to be placed as shown here. And the idea is that those rebars should be placed along the perimeter of the transverse reinforcement. The last remaining question is, what happens here in this little ledge that holds the load? We have to design that, and I'm going to show you how to design that in a future lecture, but for right now we're going to leave that for later. So this concludes the design of a beam for combined flexure, shear, and torsion.